Hello, this is Shravan. This is my video report for Milestone 1 in SE456. So here we have it. We've got our alien grid here, and as you can see, they're moving and animating at the exact same time. When you hit the end of the grid, you come down and you start moving in the opposite direction. So I'm just going to pull up the design doc real quick. And so right here, so we have our screen size. Black colors, three different types of aliens, the grid, they're moving horizontally, they bump, move down, and come back. The animations you can see here, so two images for each one of them, and the animation movement is synchronized. And okay, so yeah, all these managers are right there, and I'll just walk you through them. So with the design patterns, I'm actually going to go take like a bottom up approach here to sort of walk you through this. So the first one, let's talk about the composite pattern. This is what we use to construct the grid and move all aliens by moving this grid. So we have it here. We have our component class. We have the leaf and the composite that both derive from it. And we have these abstract methods, move and step down. And the move method is for horizontal, step down is obviously for coming down. So you can see here that we have these are all abstract methods, and they're going to be implemented in the child classes. And we also have two static variables here that just are for the size. So the movement amount, how much you move horizontally, how much you move down. So if I look at the composite class, you can just see that they're all implemented here. So the move here cycles through the list of components and calls moves over there. Step down does the exact same thing. And in the leaf, you can see here that since our game object derives from leaf, we can make it an abstract class, and that doesn't do much. But in the game object class here, the move and step down are they're defined over here. So this is how that part is working. So how we use it in action is that we have a class here called grid. This is what we use to model a root node. And so you can see here that it has a public function called move, which does all the collision detection here and steps down if it detects one. Otherwise, it moves the entire grid. And then this is propagated all the way down to each leaf, and that's how it's happening. So the advantage is that we can do all collision detection inside of here instead of doing it maybe for all objects, and we're just avoiding a lot of computation. The next pattern that we use in terms of animation is the command pattern. So we have that here, and we have two different commands. One is the movement animation, the other one is the animation sprite. We already discussed this last week. For the move one, this class points to a grid, and basically the only thing that it's doing is every time execute is invoked, it calls the grid, and that's how it moves it, and then it reattaches itself to the timer with the next delta time. And the animation sprite is pretty much what it was last week. It has a single linked list of all the images, and then over here it just cycles through those images and reattaches itself to the timer. So that's there. The next thing is proxies. So we have just three types of sprites. So we construct a proxy so that we can just have multiple objects of those same three types. So the only thing that a proxy does really is take in different x and y's and put those sprites as the different x and y's. So whenever you update a proxy, it just pushes its x and y to the game sprite that it's pointing to, and then updates and renders that game sprite. And that's how we get multiple objects of a single sprite going onto the screen. So you can see that here points to a game sprite, and then that goes ahead and for your sprite batch and SB nodes and all that, the proxy sprite derives from a sprite base. So really rendering proxy sprites is no major change at all. Finally, the last significant pattern is our object pool, which is something that we've been using since day one. You have your manager, you have your D-Link, and the manager manages a bunch of D-Link objects. It manages two lists here, the reserve and the active, and basically what we do is we do an initial land grab of resources, which is right here. This is when you create the manager, and then you simply hang on to those resources, and then every time you need something, you pull it from the reserve list, push it to the active one. When you're done with the resource, you pluck it from the active one, push it back to the reserve. And we have statistics here that can basically that we can use to find out how many nodes our application used, or how many peak nodes the application used. So next time we can just initialize these things with that amount, and that way we avoid all extraneous calls to new, and any sort of dynamic construction, and that's how we do it. So in our main program, we have our 3 game sprites, we have their corresponding animation sprites, we have the SB node managers, which is for our sprite batch, and we have the grid, we have its movement sprite as well. And we've basically modeled this entire thing into 5 rows, and each row has 11 aliens. This is how it is for now. Of course, we're going to change it and divide it up into columns later on. But basically, you're initializing all your managers. They're all singletons. We have our alien factory over here, and the only thing it does is does 3 things. It creates a game object out of a proxy sprite, attaches the proxy sprite to the sprite batch manager, attaches the game object to the game object manager, and then attaches the game object to the grid. And we have the grid being passed into the factory for now. This can also be refactored later. So anyway, so you just create the managers, attach to the sprite batch, add the textures, add the images, add all the sprites, and then here it is. You create your grid, you have your 5 rows, you use the factory to populate those rows, add them here, and that is it. So just as a last view of it, we have our entire grid, moves as one, animates in the exact same step, and as you can see, it's going to go down. It's hit the edge here and go down. There you go. And by the way, this is the screen size is where did it go? Yeah, 672 by 768, and but it's adjusted to actually work with multiple screen sizes. So we take the leftmost position of this alien and we pass in the width, and basically that way we can get this exact same sort of movement independent of screen size. So I think that's it. Thank you so much for watching, and